Hi Chemistry. Today we're going to talk about Lewis dot structures and how that they're involved in chemical bonding. We've talked about Lewis dot structures before. We've talked briefly about them in the periodic table section, and we talked about how that they were all about valence electrons. Those are the electrons in the outermost shell on the Bohr model. But those valence electrons were discussed at length by many physicists at the time. About the beginning of the 19th century, electrons surrounding the nucleus, they knew that they were in a special arrangement. And this special arrangement, chemists began to investigate different theories upon how that they were involved in the bonding. And Gilbert Lewis, this guy right here, Gilbert Newton Lewis, he was instrumental in the development of a bonding theory based upon the number of electrons in the outermost valence shell of the atom. And those electrons, that there would be a full octet. Remember that is 8 electrons in the outermost shell. There would be a full octet, and that is always involved in all of the bonding. Well, there are a couple exceptions to the rules. One of them is the hydrogen, helium, and lithium, that they only have a full duet because of the lack of electrons in their outermost shell. But also we're going to take this information, we're going to use it with our electron configuration. We're going to kind of like bring all these ideas together with this part. Well, let's go ahead and review our valence electrons. If you remember right, that's the number of electrons in the outermost shell. Well, also, if you think as you go across the periodic table, lithium right here, lithium has got 1 electron in its outermost shell. So I'm going to go up here to the top. Lithium has got 1 electron right there. Again, this should be all review. Moving over, one more. Beryllium has got 2 electrons, and I'm going to do this how my teachers taught me and how our textbook goes over it, where they are 180 degrees apart from the nucleus of the atom. And it is depicted by that representation right there. Next, we're going to go all the way across over to boron. Now there is 3 electrons coming across, 3 electrons in its outermost shell. And this one is a special column. This one here is a special family where they kind of go 120 degrees apart, because of the lack of electrons in its valence shell. Okay, carbon, going over one more. Carbon is now counting over. There is 4 electrons in its outermost shell, and it's shown this way. Okay, moving over one more. Nitrogen. Nitrogen has got 5 electrons in its valence shell. 2, 4, 5. Okay, so that's a nice depiction of that. One more, there's 6 electrons, 6 valence electrons on oxygen, so it goes like this: 1, 2, 3, 3, 4, 5, 6 electrons in its valence shell. Fluorine, 1 more electron, now there's 7, counting over 7, so it goes 1, 2, 3, 4, 5, 6, 7. Neon, neon has got a full octet. 1, 2, 3, 4, 5, 6, 7, 8. Cool. Okay, now let's go and take this information that we know. Okay, we know that boron's got this Lewis dot structure, but how is that related to the electron configuration that we know? Look at boron over here. Its electron configuration is 1s2, 2s2, 2p1. So these 2 right here are the highest energy levels, number 2. And there's 2 electrons there plus 1 more, so there's a grand total of 3 electrons in its valence shell, and there you go. Let's look at one more. Let's look at beryllium. Beryllium has got this abbreviated electron configuration down here. Here is this noble gas core, inner core, and then we've got all the rest right here. But you notice, again, 4s2, 4p5, there's 2, 5 more, so that is a grand total of 7 electrons in its outermost shell, and it'll look like this in the Lewis dot structure. So that should be a nice review there. Okay, now we need to start making structures where we are bringing these 2 together, and we're going to do it with hydrogen chloride. Hydrogen has got 1 electron in its outermost shell. Chlorine has got 7. 1, 2, 3, 4, 5, 6, 7. So you'll notice that there are alone, there's alone, that guy's all alone. And over here on hydrogen, he's all alone too. And you know the electrons like to be paired. They like to be in pairs because of their electron, remember electron orbital diagrams? They like to be in pairs. So we're going to make a bond from hydrogen to chlorine. Okay? Now that's really cool because if you look at chlorine, it's sharing those 2 electrons in that bond. So if it's got 2 electrons right here in this bond, 2 more, and 2 more, so that's a grand total of 8 electrons in its valence shell, or valence electrons. And hydrogen, it's got a full duet when you count those 2 electrons in its bond too. Okay. Oh, here's a better diagram of it. Okay. Notice shared pair of electrons right here, and these are here all lone pairs, lone pair, and a lone pair. Okay, now we're going to do the same exact thing but for ammonia. Now I've got to figure out my central atom. Okay, my central atom is definitely nitrogen. Okay, so we'll draw nitrogen right here. Nitrogen is the central atom, so that means that there's going to be 3 hydrogens around it. And if you add up the number of valence electrons, look at this. Nitrogen has got 5 around it. I'll go ahead and draw them on there. 1, 2, 3, 4, 5. Okay, it's got 5 valence electrons. Hydrogen has got 1. Well, there's 3 of them, so I got to times it by 3, so that's going to be 3 plus 5, so it's going to be a total of 8 electrons. So we'll double check that later on. I sometimes forget to do that, but it's important to do that so that you can double check your work and see if you're doing it correctly. Okay, now we're going to put all of our atoms on here. So we've got 3 hydrogens. Well, look at that. We've got 3 electrons. They're just all alone on nitrogen. Okay, so we're going to connect them all now with a bond. I'll do that in blue. Now, count your bonds. Take that number times 2, because there's 2 electrons in each bond. So there's 6 involved in all the bond and electrons, plus the 2 more in the lone pair of electrons. So that makes a grand total of 8 electrons. So we can double check. And we have got a full octet around nitrogen, full duets around hydrogen, so that's a very good diagram. And I think I've also got the picture that looks much better than my drawing right there. Notice that there's 8 electrons on it. Okay, here are the exceptions to the rules. Beryllium, again, a lack of electrons, and boron, lack of electrons. But phosphorus and sulfur and xenon, they can have multiple bonds, and I really don't do much with them for your class. These bottom 2, okay? We do a little bit with the sulfur, but we expect it to have a full octet for just practical use of being able to write out the correct Lewis dot structure. Okay, let's look at carbon dioxide up here. Carbon dioxide, what's the central atom? Well, we look for the least electronegative, so that is definitely going to be carbon. Okay, count up the valence electrons. Carbon has got 4 electrons on it. Okay, and oxygen has got, but there's 2 of them. Oxygen has got 6 electrons on it, but we got to multiply that by 2, so there's 12 there, plus the 4 more, so it's a grand total of 16 electrons. Okay, now we're going to go ahead and draw the molecule. We're going to draw a carbon in the center, and it's got its 4 electrons around it. And here we'll put oxygen right here, and oxygen right here. Okay, it's got, oxygen has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, we'll show the bonds in red. Here's one. Here's one. Those ones are the easy ones, but look at these. I see this one, and it's contracted here. And you got to remember that these are 2-dimensional drawings for actually 3-dimensional molecules. Okay, well, let's go ahead and check out our valence electrons. We've got 4 bonds, and 4 times 2 because there's 2 electrons in each bond. That's right, there's 8. And we also have 8 more electrons for a grand total of 16 electrons on our whole drawing. Let's go ahead and draw this prettier. Okay, so here's this. We got 2 double bonds coming off of carbon on both sides. Attached to some oxygen. There's 2 lone pairs on each oxygen. So that's what it looks like when it's all cleaned up and nice and pretty. Okay, let's try it on these molecules. Go ahead and pause it now, and I will put the correct answer on here. So I want you to pause it now. And I will pause mine and draw all the correct ones on there so you can check them real quick. Okay, check your work. Also, I've double check all the electrons. Make sure that you've got them all written out. Double check the electrons. That's a great way of checking your work and making sure that you've done it right. Well, that is all for now. I will see you in the next segment.